In a previous video, we saw that as we did more and more iterations of Koch's snowflake curve, that the length of the curve, or perimeter of the curve, tended toward infinity. What we're going to see in this video is that as we do more and more iterations of the curve, that the area of the region enclosed by the curve is actually finite. So what we're going to do is we're going to find the area, AN, which is the area enclosed by the curve CN, and show that the limit as n tends to infinity of AN is equal to 8 over 5 times A1. So we'll start by finding the area enclosed by the curve C1, which is given by A1. So if we look at our curve C1, that's the equilateral triangle that we've started with. So we've got side lengths S, and we know that if we've got an equilateral triangle, that all the angles in that triangle are going to be pi over 3 radians or 60 degrees. So we know two sides of the triangle and the angle between them, so we can work out its area by using this fact here, which I'll write up at the top right corner of the screen. We know that the area of a triangle, given that we know two sides and the angle between them, is equal to half times A times B times sine C, where A and B are the lengths of the sides of the triangle and C is the angle between them. So for our one here then, A and B are both equal to S, both of the sides are equal length, and C, the angle between them, is pi over 3 radians. So we get then that A1 is going to be equal to half times S, so S squared times sine of pi over 3, and sine of pi over 3 is square root of 3 over 2, so this then is equal to half times S squared times square root of 3 over 2. So A1 is equal to square root of 3 over 4 times S squared. Now the number of new triangles at each iteration is equal to the number of sides of the previous iteration. So to see why that is, if we look at curve C1, say this side here, well, in curve C2 we divided that line into 3 equal line segments and made our outward pointing equilateral triangle. So that side there, we added on one new triangle in C2, and that's going to be true of every side, and that's going to continue on at each iteration. So each side of the previous iteration, when we come to the next iteration, it's going to have one new triangle added onto it. So we found in a previous video, when we were looking at the length of the curve of Koch's snowflake, that the number of sides at Cn is equal to 3 times 4 to the power of n minus 1. So we'll note that down. So the number of sides at the previous iteration, well, that's given by Cn minus 1, is going to be equal to, so wherever we see n in that above formula for the number of sides at Cn, we're just going to replace it with n minus 1. So we get then Cn minus 1 is equal to 3 times 4 to the power of n minus 2. Now the area of each new triangle, to find out what that is going to be equal to, we can look at the area for A1, which is root 3 over 4 times S squared, and just replace that S with S over 3 to the power of n minus 1. So we get then the area of each new triangle is equal to root 3 over 4 times S over 3 to the power of n minus 1 all squared. So to see why that is, if we look at a line segment on C2, say this one here, well, the length of that is going to be 1/3 the length of the sides at C1. So this length here is going to be S over 3. So in C2, all those side lengths are going to be S over 3. And at C3, say this side here, well, that's going to be 1/3 the length of the sides at C2. So the sides at C3 then, they're going to be S over 3 times 1 over 3, because they're 1/3 the length of the sides at C2, that's going to be s over 3 squared. So that's why we've got that s over 3 to the power of n minus 1 all squared there. So the total area of all the new triangles at each iteration, well, that's going to be equal to the number of new triangles at each iteration, which is given by 3 times 4 to the power of n minus 2, times the area of each new triangle, which is root 3 over 4 times s over 3 to the power of n minus 1 all squared. So A2 then, well, that's going to equal A1, because we're still going to add on this triangle here that we have from curve C1. We're going to add that area on, plus the area of all the new triangles. So what we're going to do is the area of all the new triangles was given by this formula here. So we're just going to plug in n equals 2 into that formula and go from there. So what we're going to get then is it's going to be plus 3 times 4 to the power of n minus 2. So to the power of 2 minus 2, which is just the power of 0. So that is just going to equal 1. So we're going to get then plus 3 times square root of 3 over 4 times s over, well, 3 to the power of n minus 1 is 3 to the power of 2 minus 1, which is just 3 to the power of 1, and that's just equal to 3. So we get s over 3 all squared. So we'll just write that out in full. So A1 was given by root 3 over 4 times s squared, and then plus our 3 times 3 root 4 times s over 3 all squared. So A3 then, well, that's going to be equal to A2 plus the total area of all the new triangles at curve C3. So that's going to be equal to then 3 times 4 times square root of 3 over 4 times s over 3 squared all squared. So we just plugged n equals 3 into that formula for total area of all the new triangles. So I'll just write this out in full, so then we can start seeing a pattern forming. So A2, well, that was equal to root 3 over 4 times s squared plus 3 times root 3 over 4 times s over 3 all squared, and then we had our 3 times 4 times root 3 over 4 times s over 3 squared all squared. So A4, well, that is going to equal A3 plus 3 times 4 to the power of 2 times root 3 over 4 times s over 3 to the power of 3 all squared. So we won't write this one out in full, but we can start seeing the pattern that is forming now. So each term that we add on, this 4 here, the power that we raise it to is going to increase by 1 each time, and this 3 in the denominator here, the power that we raise that to is also going to increase by 1 each time. So what we get then in general is an is equal to root 3 over 4 times s squared plus 3 times root 3 over 4 times s over 3 all squared plus 3 times 4 times root 3 over 4 times s over 3 squared all squared plus, and we just continue on, and each term thereafter, that 4, the power we raise it to would increase by 1, and that 3 in the denominator here, the power we raise this to would increase by 1, and we keep going until we get to 3 times 4 to the power of n minus 2 times root 3 over 4 times s over 3 to the power of n minus 1 all squared. So we can start to simplify this now. So we can notice that this root 3 over 4 occurs in every term, and also the s squared is common to every term as well. So we can factor those out. So we have then that an is equal to root 3 over 4 times s squared, and then in brackets we're going to have 1 plus 3 times 1 over 3 all squared, and then plus 3 times 4 times 1 over 3 squared all squared, and we're going to continue on, and then we get to plus 3 times 4 to the power of n minus 2 times 1 over 3 to the power of n minus 1 all squared. So we can simplify this a bit more by noticing that this 1 over 3 to the power of n minus 1 all squared is equal to 1 over 3 to the power of 2 times n minus 1, which is equal to 1 over 3 squared all to the power of n minus 1, and that is equal to 1 over 9 to the power of n minus 1. So we have then that an is equal to root 3 over 4 times s squared, and then in the brackets we're going to have 1 plus 3 times 1 over 9, and then the next term we're going to have plus 3 times 4 times 1 over 9 squared, and then I'll just write out one more term so it's clear what the pattern is. Then we're going to have plus 3 times 4 squared times 1 over 9 cubed. So each successive term, the power of 4 is going to increase by 1, and the power of 1 over 9 is going to increase by 1. So that's going to continue on up to plus 3 times 4 to the power of n minus 2 times 1 over 9 all raised to the power of n minus 1. So we've got our formula for an looking a bit neater now, and in the next video we'll continue to simplify it even further, and then we'll show that the limit as n goes to infinity of an is equal to 8 over 5 times a1.